Hi, my name is Talia, and I'm a high school senior. I love teaching others about chemistry and math, and this YouTube channel is a supplemental resource to anyone who may be needing some extra help in their chemistry classes. This week, I'm going to be talking about empirical and molecular formula, so if you need help with that topic, feel free to continue on watching, and without further ado, let's get started. So I'm going to first explain the difference between an empirical and molecular formula. So the empirical formula is the simplified version of a chemical formula, and it shows the ratio of atoms of each element. So it's like if you were to simplify the fraction 8/10 to 4/5. 4/5 is divided by 2, and it is simplified. Then we have the molecular formula, which is like the 8/10. It is the naturally occurring formula of the compound, and it shows the actual number of atoms of each element. And you can simplify the molecular formula in order to get the empirical formula. So an example is glucose. So if we look at the molecular formula, it is C6H12O6, but all of these subscripts have a common factor, which is 6. So if we reduce by 6, then we get CH2O. 6 divided by 6 is 1, 12 divided by 6 is 2, and 6 divided by 6 is 1. So this is our empirical formula, which is reduced. So then we can also find the molar mass of both the empirical and the molecular formula. And the molecular formula molar mass will be a multiple of the empirical formula's molar mass, because the molecular formula is just the empirical formula times a number. If the molecular weight is 4 times the empirical weight, that means that the molecular formula is 4 times the empirical formula. So that is the number you would multiply the empirical formula by in order to get the molecular formula. So we are going to determine the empirical formula from the molecular formula. So if we look, we have N4S4. The common factor in both of these is 4. So we can divide by 4 and get NS, because 4 divided by 4 is 1. Then we have C5H10. The common factor in each of the subscripts in this compound is 5. So you can divide by 5 and we get CH2. Now I can show you how the molar mass of the molecular formula would be a multiple of the molar mass of the empirical formula. We can take C5H10 and CH2 as an example. So C5H10, we have 5 times 12.01 plus 10 times 1.008, and then we have 70.13 grams per mole. Now, if we do the same thing with CH2, we have 12.01, because there's only one carbon, plus 2 times 1.008, we get 14.026. Now, to see the multiple, we would divide the larger molar mass by the smaller molar mass. So I have 70.13 over 14.026, and I get 5. And that is exactly what we multiplied the empirical formula by in order to get the molecular formula. So this number comes back into play here in order to get to here. So it's all kind of just one big circle of numbers. So now we are going to practice determining the molecular formula from the molecular weight, just a continuation of the example I just showed you. So if we have an empirical formula of NH2 and a molecular weight of 32.052 grams per mole, we now have to determine the molecular formula. So I'm going to do what I just did in my example. First, calculate the empirical weight. I'm going to abbreviate that as EW. So I have 14.01, which is the molar mass of nitrogen, plus 2 times 1.008, and then that gives me 16.026 grams per mole. So now if I divide the molecular weight by the empirical weight, I get 32.052 over 16.026 to get 2. So now to write the molecular formula, I'm going to take that number, and that is the number I'm going to multiply the empirical formula by, and I'm going to get NH2 times 2, which equals N2H4. So that is our molecular formula, which we determined from the molecular weight. So now I'm going to show you how to determine empirical formula when you're given like masses of different elements in a compound. So it's determined from the percent composition of each of the compounds. And you can watch my previous video on percent composition if you need more instruction about that. So I have an example courtesy of Sarah Lipitz, and this compound contains only calcium, carbon, and oxygen. We have a total of 34.5 grams, and there are 13.8 grams of calcium, 4.2 grams of carbon, and 16.5 grams of oxygen. So we are going to determine the empirical formula. I personally like to do this with a table where I have elements, mass, moles, and the ratio. So first I put each of the elements in the first column. I have calcium, carbon, and oxygen, and then I write the mass of each of them. And then I determine the moles by dividing the mass by the molar mass. And then, so after I have the moles of each of the elements, I divide the moles of each of the elements by the smallest number of moles. So in this case, the smallest number of moles was calcium. So I'm going to divide the moles of each element by 0.34. So if I divide 0.34 by 0.34, I get 1. If I divide 0.35 by 0.34, I get about 1. And if I divide 1.03 by 0.34, I get 3. So I also made a note that we only use 16 grams for oxygen, not 32, even though it's a diatomic element, because in the compound, it is not written as O2. The compound contains calcium, carbon, and oxygen, and diatomic elements are only written with the 2 subscript if they are by themselves, or if the compound requires 2 of them. But in this case, we're just going to divide by the molar mass of 1 oxygen. So then with this, I can write my empirical formula using the ratios. I have CaCO3 because I have 1 calcium, 1 carbon, and 3 oxygens. So there might be instances where you are not just given like 14.8 grams of this element. One that is very common is when you are given percentages of elements within a compound. So for instance, if you are given that a compound is 66% carbon, the process for finding the mass of that, because you cannot solve this table without the mass, is to set the total mass equal to 100 grams, and then just 66% becomes 66 grams, 78% becomes 78 grams, etc. Because 78 grams is 78% of 100, it works out perfectly, and the 100 will not mess up your empirical formula. So there is also a process if your ratio for an element, so like one of these numbers, is not a whole number, you would basically just multiply all of the ratios by the number that you use in order to get rid of the non-whole number. And I will show you over here. So if one of your ratios ends in 0.25, you are going to multiply all of the ratios by 4. If it ends in 0.33, you multiply by 3, 0.5 multiply by 2, 0.67 you multiply by 3, 0.75 you multiply by 4. And remember, you multiply for all the ratios. So like if you have 1.2, like over here, if we had 1.25 for calcium, 1 for carbon, and 3 for oxygen, we need to multiply calcium by 4, carbon by 4, and oxygen by 4, because what you do to one element needs to be done to all of them. Okay, so now we are going to move on to the determination of a molecular formula. So just adding an extra step to the example I just showed you. So like our example previously, it can be determined from the empirical formula and the molecular weight. So we have another example where we have a 44.680 gram sample of white powder that contains 19.58 grams of phosphorus and 25.28 grams of oxygen. The molecular weight is 283.88 grams per mole, and we are determining the empirical and molecular formula. So if we make our table, and we can divide it up, we have phosphorus and oxygen. And then in our mass column, we have 19.58 grams phosphorus and 25.28 grams oxygen. Now we are going to convert them both to moles. So if you multiply 19.58 grams times 1 mole over 30.97 grams, which is the molar mass of phosphorus, we're going to get 0.632 moles. And then if we do 25.28 grams and we want to convert it to moles of oxygen, we're going to divide by 16, not 32, because the oxygen is not alone in this case. So now we have 1.58 moles oxygen. And now we are going to do a ratio. So you are going to divide each amount of moles by the smallest number of moles, and our smallest number of moles is 0.632. So in this column, we are going to do 0.632 moles over 0.632 moles to just get 1. Here we are going to do 1.58 moles over 0.632 moles. And this gives us a ratio of 2.5. So now that is not a whole number. So if we go back to our chart, if we have a 0.5, we need to multiply both of these by 2. So if I multiply 2.5 by 2, I get 5. And if I multiply 1 by 2, I get 2. So our empirical formula is P2O5. Now we have our molecular weight and we need to find our molecular formula. So we need to find the empirical weight. So 2 times 30.97 plus 5 times 16 is 141.94 grams per mole. And if I divide the molecular weight by the empirical weight, I'm going to get 283.88 over 141.94. Which gives me exactly 2. So now we know that number we have to multiply by. So for our molecular formula, we're going to multiply P2O5 by 2 to get P4O10. That is our molecular formula for this problem. Now we are going to talk about the empirical formula of a hydrate. This is a super small addition to what we've already learned. So basically, when you're finding the empirical formula of a hydrate, you add a hydrate to a crucible and you evaporate all of the water off of it to get just the mass of the salt. And then you do more subtraction in order to get the moles of the salt and the moles of the water. And then you can calculate the amount of the hydrate there is. Okay, so when we're calculating the empirical formula of a hydrate, we're going to want to get the number of moles of the anhydrous salt and the moles of the water driven off, and then we are going to divide those two in order to get a factor similar to how we do with molecular weight and empirical weight, and that is going to tell us how many water molecules are in the hydrate. So we have all this whole data table with information that we are going to fill in order to calculate the empirical formula of the hydrate. So if we have the mass of the empty crucible as well as the mass of the crucible plus the hydrate, the mass of just the hydrate will be 5.00 grams. Then we heat the crucible so that the water evaporates, and we heat it twice in order to make sure all of the water has evaporated off. So if we want to get just the mass of the anhydrous salt, we are going to subtract the mass after the second heating from the mass of the empty crucible, because after the second heating, we have just the salt and the crucible. And if you subtract that from the crucible, you are going to get just the mass of the anhydrous salt. Finally, we want to find the mass of the water driven off. So that is going to be the mass of the hydrate minus the mass of the anhydrous salt. Because if you think about it, the hydrate had the water in it and the anhydrous salt does not. So we would subtract those two to get the mass of the water. Okay, so now we are going to calculate the moles of the anhydrous salt. And we know that the anhydrous salt is CONO3 3. So we have mass, 3.47 grams, and we are going to multiply by the molar mass, which is 244.96 grams per mole. I'm putting it on the denominator so the grams can cancel out. And that is going to give me 0.0142 moles of CONO3 3. Now we're going to calculate the moles of the water driven off. So we have 1.53 grams of water, and the molar mass of water is 18.016 grams. So I'm going to convert to moles and get 0.0849 moles of H2O. And I forgot to mention this, but this problem is also courtesy of Sarah Lipitz. And finally, we are going to calculate the ratio of moles of water to moles of anhydrous salt. And that is going to help us determine the empirical formula. So if we divide 0.0849 moles over 0.0142 mole, we get 6. That means that there are 6 water molecules per cobalt-3 nitrate molecule. So then our empirical formula is going to be CONO3 times 6H2O, which would be written as cobalt 3 nitrate hexahydrate. Now we are going to do some individual practice with empirical and molecular formulas. This is using the percentage method that I talked about earlier. So as a hint, remember to set your total mass to 100 grams, and then you can just make each of these percentages a mass. So we have 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen. You have the molecular weight is 176 grams per mole. You want to calculate the empirical and molecular formula for absorbic acid. So give that a try, and then we're going to go over it together. Okay, so let's go over the answer. I set my total mass equal to 100 grams. So that means I have 40.92 grams of carbon, 4.58 grams of hydrogen, and 54.50 grams of oxygen. I'm just using my table once again. So then I'm going to convert each of the masses to moles, where I get 3.41 moles carbon, 4.54 moles hydrogen, and 3.41 moles of oxygen. And then, just like previous problems, I'm going to divide each amount of moles by the smallest number of moles, which is 3.41. So then I have 1 carbon, 1.33 hydrogens, and 1 oxygen. And the hydrogen ratio is not a whole number. So I'm going to multiply everything by 3 to get my empirical formula of C3H4O3. Now to get my empirical weight, I just do 3 times 12.01 plus 4 times 1.008 plus 3 times 16 to get 88.062 grams per mole. Now I want to get the number that I multiply the empirical formula by. So I take the molecular weight, 176 grams per mole, divide by 88.062 grams per mole to get 2. And that is what I'm going to multiply the empirical formula by to get a molecular formula of C6H8O6. That is our example problem and the end of the discussion for this week. I hope you enjoyed this week's video. Next week, I'm going to be jumping into a new unit about chemical reactions, so feel free to watch next week if you need some additional help. I'm going to leave a link in the description box to my website if you would like to schedule tutoring with me, and I am also able to answer any questions you have in the comments, so feel free to leave them if you have them. I hope you enjoyed this week's video, and good luck with learning the rest of your chemistry.